Organic Chemistry, Chem 212, Exam 4 Material, Part 5. Reactions of alkyl halides, nucleophilic substitutions, and eliminations. Alkyl halides react best with nucleophiles and bases. Alkyl halides are polarized at the carbon-halide bond, making the carbon electrophilic. Nucleophiles will replace or substitute the halide in the CX bonds of many alkyl halide reactions. The reaction is a Lewis base. We can see that the nucleophile is going to come in. It's going to be attracted to this carbon. Now this one isn't showing you the dipole, but remember back up here when we have a halogen on there, our carbon has a slight positive charge, and we can see that the electron cloud's being pulled towards the halogen, and it's going to have a slight negative charge. So this negative nucleophile is going to be attracted to this carbon. The pair of electrons is going to go ahead and go to this halogen, so it's going to go ahead and be an anion in this case. And the two electrons from our nucleophile is what's bonded to the carbon. That's where these two electrons came in for this bond. Nucleophiles that are Bronsted bases produce an elimination reaction. When the nucleophile comes in, it can attack the proton, or the hydrogen in this case, in an elimination reaction. The nucleophile is now going to be bonded to the hydrogen, but the pair of electrons that were between the hydrogen and the carbon are now going to be given to the carbon-carbon bond, forming an alkene. When the pair of electrons goes here, that gives too many bonds to our carbon, so the pair of electrons that held the carbon and the halogen, well, that pair of electrons is going to go to the halogen. We have a new alkene, and our nucleophile now is attached to our hydrogen. So the net result is we expelled the halogen and eliminated it, causing a carbon-carbon double bond. The discovery of the Walden inversion. In 1896, Walden was able to perform a cycle of reactions that interconverted negative malic acid and positive malic acid. This led to the research of nucleophilic substitution reactions. The reactions alter the array at the chirality center. The reactions involve a substitution at the center. Therefore, nucleophilic substitution can invert the configuration at the chirality center. Stereochemistry of nucleophilic substitution. Through more experiments, they found that the inversion occurs in the second step of the reaction during the nucleophilic substitution step. Substitution, by definition, requires that a leaving group, which is also a Lewis base, departs from the reacting molecule. A nucleophile is a reactant that can be expected to participate effectively in a substitution reaction. Here we have our alkyl group with our X. Now here's something interesting. We have chlorine, bromine, and iodine as our X here, and usually X represents a halogen, but it's also going to represent this tosylate. O-tos is this entire structure here, but you will often see it as O-tos. It's a lot easier to draw than this whole structure. But let's take a closer look at this. This is where the oxygen would be bonding to the carbon group, and this makes a fantastic leaving group. If you want a reaction to happen, then you want one group to leave, so a great leaving group is definitely a nice thing to have. We have oxygen, and next to it is a sulfur, and that sulfur has a bunch of bonds around it. In fact, it has 6 bonds around it. Benzene ring, and on the other side of where the sulfur attaches here, we see a CH3 group. Be sure to add this to your functional groups that you know. So let's take another look at the reaction. So Rx, which could be any of these things here, will react with a nucleophile, and nucleophiles tend to have a lone pair of electrons, and the best nucleophiles are negatively charged, but some are neutral. What's going to happen in this reaction is a substitution where the nucleophile is now bonded wherever that halogen or that tosylate was. How the inversion happens. There's 2 stereochemical modes of substitution. You can either have an inversion or retention. Inversion, if you take a look at the rankings of these 1, 2, 3, 4, and this one here happens to be an S, the nucleophile comes in, and when it attacks, it actually inverts the whole thing, And now instead of us having the S, we actually have an R. We can also have substitution with retention, where we just simply have the X group replaced with the nucleophile, and that's retention. The kinetics, or the rate of reactions of nucleophilic substitution. Kinetics of reaction is the relationship of the reaction rate with concentration. A rate constant, K, is the proportionality factor between concentration and rate. Rates decrease as concentrations decrease, but the rate constant does not. The rate units, they're concentration over time, and so typical units would be liters per mole per second. A rate law describes relationship between concentration of reactants and conversion to products. This is a result of the mechanism. The order of the reaction is the sum of the exponents of the concentrations in the rate law. The example below is a second-order reaction. In a second-order reaction, the rate is linearly dependent on the concentration of the two species. Rate equals the rate of disappearance of the reactant. Rate equals K times the concentration of Rx times the concentration of the nucleophile. The rate law of this reaction would be specifically K times sodium concentration of sodium hydroxide, our reactant, and our other reactant with CH3Br. The SN2 reaction. SN2, S stands for substitution, N for nucleophilic, and 2, it's bimolecular. 2 steps combined without an intermediate. Sometimes I've seen SN2 with the N not subscripted, so you'll probably see it in both ways. So we have 2 steps combined without an intermediate. This occurs with primary and secondary alkyl halides. The reaction occurs with an inversion of stereochemistry. So if you start off with an R, you end up with an S. SN2 reactions follow second-order reaction kinetics. The rate law would be K times the concentration of the nucleophile and the concentration of our original alkyl halide. SN2 process. The reaction involves a transition state in which both reactants are together. This requires the entering nucleophile attack the halide from a direction 180 degrees away from the leaving group. This causes an inversion of the configuration at the carbon atom. Our nucleophile comes in at 180 degrees away, so it actually attacks straight in. But remember, when we're showing a mechanism, we have to use curved arrows to show that 2 electrons are coming in. So that's why a curved arrow is used here. But it's actually a 180-degree attack opposite our halogen. The nucleophile is going to contribute the pair of electrons to bond to this carbon, and it's going to cause these other 3 groups to flip over. And then the pair of electrons that was holding on to the halogen are going to both be given to the halogen. So we have an inversion is going to happen. Examples of nucleophiles, they're all listed here. Be sure to learn those. And again, a nucleophile has a lone pair of electrons, can either be negative or neutrally charged. Here's an example of an SN2 reaction with inversion. Our nucleophile, OH, attacks from the backside here. It's going to cause these guys to flip over. The OH is attached, the Br is separate. We went from an S to an R. Let's look at the mechanism for SN2 to get a better idea of why we get an inversion. Mechanism of SN2, the transition state is planar arrangement of the carbon atoms and the 3 remaining groups. When the nucleophile comes in 180 degrees here, this is the bimolecular piece we're talking about for SN2. This transition state is one that's going to be very important. In fact, I use this as my reference point for me to help make it clear on the difference between SN1 and SN2, and then we're also going to see the elimination, E1 and E2. This transition state is key. We have attached at the exact same time our nucleophile that came in 180 degrees attached to this carbon, and then the leaving group, Y, that's what this is talking about, this is our leaving group here, is attached at the same time. Because these 2 pieces are attached at the same time, those 3 that were not involved in the reaction, they end up becoming planar. Then what happens is the Y group leaves and an inversion happens. During the transition state, the negative charge is delocalized over both the nucleophile and the leaving group. Characteristics of the SN2 reaction. The rate of reaction is determined by delta G, the energy difference, the reactant ground state, and the transition state. In this first example, following the delta G, we have a decrease in the reaction rate because we have such a big difference here between the ground state and the transition state. In the second example, we have a decreased delta G, which increases the reaction rate because it has a lower energy barrier it has to overcome. Steric effects are important in an SN2 reaction, and this is because we have that 180-degree backside attack. So if we have a lot of R groups, a lot of carbons on the carbon that we're trying to react with, then it gets in the way. So steric effects always have to do with physically something's in the way. The more alkyl groups connected to the reactant carbon, the slower the reaction. Steric effects destabilize the transition states. Severe steric effects can also destabilize the ground state. Looking at this reactivity relative to each other, neopentyl, they're counting that as their baseline, their number one. So for every one of these that react, we have less than one of the tertiary reacting. So the neopentyl, take a look at this group here. We have 5 carbons on here total, 1, 2, 3, 4, 5, and my bromo is attached to this end carbon here. A secondary carbon is going to react 500 times more than the neopentyl. We don't have as much stuff in the way. It's not sterically hindered. And the less R groups we have, all the way to the methyl is 2 million times more likely to react than the neopentyl. We don't have so much stuff in the way. So again, this down at the bottom shows us relative reactivity. On the next slide, we'll have a graphic that represents the steric effect pretty nicely. So this is a methyl group. There's really nothing in the way, just hydrogens for the 180-degree attack. The more R groups we get, this one is a primary, this one is secondary, and this one's tertiary. See how these 3 methyl groups basically get in the way? It's a steric effect where we can't actually have the backside attack happen as easily as when it's more exposed in this example. Again, steric effects are huge with SN2 reaction, so that's actually going to keep some reactants from undergoing an SN2. Vinyl halides, which are carbon-carbon double bonds, and aryl halides, those that have an aromatic ring, are unreactive to SN2 due to steric effects. It can't come in 180 degrees from there. This carbon here, it is at a 120-degree bond angle, and I can't get to this 180 degrees away. So this would be no reaction. This would not undergo an SN2 reaction. With the aryl halide, this is the carbon that's going to react, and this nucleophile just cannot fit inside of this ring here in order for the reaction to happen. So this would be a limitation of an SN2 reactions because of steric effects. Vinyl halides, aryl halides are unreactive. The attacking nucleophile. Neutral or negatively charged as long as it has an unshared pair of electrons. A neutral nucleophile will acquire a positive charge. The neutral nucleophile gives its pair of electrons to this R group, and then the pair of electrons that were bonding these two together go to the Y, and now we have a positively charged nucleophile. A negatively charged nucleophile will become neutral. Here's the negative sign, here's its lone pairs. It's going to give a pair of electrons to this R, so that will be now bonded to the R, while the pair of electrons holding the R in the leaving group go to the leaving group. We now have a neutral product. In an SN2 reaction, we can look at the relative reactivity of nucleophiles. Which ones are better or worse? The nucleophilic trend is the more basic it is, the more reactive it is. Reactivity increases going down the column of a periodic table, and negative nucleophiles are more reactive than neutral. So here we have the reaction here, and they're telling us the best nucleophile, SH, and then our C, remember this is a triple bond N minus, our cyanide, iodide, and then as we go down, we'll see these are less and less reactive. So we looked at the fact that the carbon gets attacked 180 degrees away, so the carbon itself, it can't be too big to get in the way, steric effect. FX, and then the nucleophile itself that's coming in, because remember the nucleophile is going to be attached to the carbon at the same time as the leaving group. The nucleophile, there's certain nucleophiles that are better than others. And now that leaving group, we want a leaving group that really wants to get out of there. So the larger it is, if we're talking about halogens, the less tightly held it is there. So it's a great leaving group. And as we mentioned before, that tosylate, best leaving group ever. A good leaving group reduces the barrier to a reaction. It stabilizes a negative charge and is a weak base. So this graphic came from your textbook, and it tells us that these are less reactive and these are more reactive. But actually, it's not a very good chart because only chloride, bromide, iodine, and tosylate work with an SN2 reaction. So they really should have left the other part of this off. This part here shouldn't even be here because along with it in your textbook, it tells us if a group is very basic or very small, it prevents the reaction and is a poor leaving group. So you can see these guys here are also listed here. These compounds do not undergo an SN2 reaction. So if we're looking at the best leaving groups, these guys aren't even leaving groups at all. They don't even come into play. Chloride, bromide, iodide, notice the larger the halogen, the better the leaving group. And then again, tosylate. So now we have to talk about where this reaction is happening. What solvent would we want to have this SN2 reaction in? The worst solvent is a protic solvent. Those that contain NH, OH, and SH group. Because what they do is they slow down the reaction by causing solvation. Solvation is when the solvent molecules cluster around the reactant nucleophile. So if you can picture what's happening here is if we have a protic solvent, it will surround the nucleophile and basically cause a barrier so it can no longer get towards the reacting carbon. It can't get there. So the best solvents in an SN2 reaction are polar aprotic. So we want the polar piece, but we want it to not have that hydrogen there. That's what aprotic is. They have strong dipoles that don't contain NH, OH, or SH. And in fact, they can increase the reaction rate by raising the ground state energy of the nucleophile. So the best solvents on this chart, they're on the right-hand side. You can see this one is 200,000 more times reactive than methyl alcohol. So we have water, DMSO, DMF, CH3CN, and HMPA being the best solvent comparatively. The SN1 reaction. SN1, the S is substitution, N is nucleophilic, and in this case it's unimolecular. Two steps with a carbocation intermediate that involve the departure of a leaving group prior to the addition of the nucleophile. This occurs in tertiary, allyl, and benzyl. Remember, SN2 is better for primary and secondary, so now we're seeing a substitution that's really good for tertiary and some other stuff. This reaction occurs with the racemization of configuration at the carbon atom. You actually get both R and S. So on the previous SN2, you got stereochemically an inversion, so an R went to an S and so on. In this reaction, because we have a carbocation, we get both R and S. This is a first order kinetics law. The rate is K times the concentration of the alkyl halide, and that's it. The SN1 reaction occurs when the substrate spontaneously dissociates to a carbocation in a slow rate determining step, followed by a rapid attack of the nucleophile. On the top part here, we show the alkyl halide, and this is a slow step. The carbocation is formed, and in the fast step, the nucleophile comes in, and now we have a substitution for the nucleophile where the leaving group was. Down here, it's showing us a mechanism in a little more detail. The pair of electrons are going to go to the leaving group in this rate limiting step. So it says that this is a slow step. It's slower than the other step, so this is our rate limiting step. And what's going to happen? See, the arrows are going in equal direction. It's just as likely for the leaving group to leave as to come back. But if it does leave, we then form our carbocation. And it's during this step that our nucleophile can come in. And we're using water as our nucleophile example here. the nucleophile will go ahead and bond to this carbocation here. In this, continuing on with this, it is again as a fast step here, because once the carbocation is formed, this thing happens almost instantaneously. Another water molecule can grab this hydrogen, forming a hydronium ion, and then the alcohol piece can be there. So this is an SN1 mechanism. We're using water as our nucleophile, but it could be any nucleophile that can undergo this. So what's our rate limiting step for an SN1 reaction? The overall rate of the reaction is controlled by the rate of the slowest step. That's your rate determining step. And that happens to be the formation of the carbocation. We start off here with our reactants in our nucleophile. Here's delta G. K1 is the first transition state. The carbocation is formed here, so it takes an awful lot of energy to get to this point. The second transition state, after you have our carbocation intermediate, needs a little bit of energy, but it's much quicker. Over here, I have the reaction written in line form. I wanted you to see this when the carbocation gets in there. So we have our X, our leaving group. This minus X means in our first step, K1, our halogen is leaving, or our leaving group is leaving, forming a carbocation. And in this second step, K2, our second transition here, our nucleophile comes in as now attached. The stereochemistry of an SN1 reaction. The planar intermediate leads to the loss of chirality. We have a free carbocation that is achiral. A racemic mixture is made since the attack can happen on either side. So when we tell you it's a racemic mixture, the true definition of a racemic mixture is half of one and half of the other, but it's not going to be 50-50 in this case. And this is due to the limitation of the leaving group being in the way. So it is rarely a 50-50% since attack can be shielded by the leaving group or remain associated with the carbocation and kind of stay in the way. So what they found experimentally is you get 60% inversion and 40% retention. When the nucleophile has an opportunity to go to the free carbocation, it can either come from the left side or the right side because this is going to be a planar carbocation. In reality, this is my leaving group here. See this one here? That's the leaving group. So it's trying to get out of there, but it's going to block or shield the nucleophile from coming in from this side some of the time. In fact, we see that 40% of the time it can actually come in here, but 60% of the time it's going to come in from this side. So we have 60% inversion, 40% retention. That's the stereochemistry of an SN1 reaction where a carbocation is formed. Here's a reaction summary. Our nucleophile comes in, 60% inversion, 40% retention. Predict the products of the reaction. Go ahead and pause the video and come back and check your work. 60% inversion, 40% retention. How'd you do? Some of the characteristics of an SN1 reaction. Tertiary alkyl halide is the most reactive by this mechanism. That's because it's controlled by the stability of the carbocation. The more stable the carbocation, the faster the reaction. So we're looking at carbocation stability. The most stable carbocation is tertiary, then secondary, which is pretty much equal to benzyl slightly less, which is pretty much equal to the allylic carbocation, and then the less R groups we have, primary, and then methyl. So an SN1 reaction, tertiary carbocations formed are the best. So to form a carbocation, we have to have a leaving group. So the effect of the leaving group on an SN1 reaction, we want a great leaving group. We want that leaving group to get out of there so the carbocation can form. That's in that slow rate determining step. And then the fast step, nucleophile comes on in. So let's look at this. The rate of reaction is critically dependent on the leaving group. The larger halide ions are better leaving groups. The most stable are conjugate bases of strong acids. So we see the halogens increasing in size, better leaving group, and tosylate is the best. So now let's look at the nucleophile in the SN1 reaction. The rate determining step was the formation of the carbocation. because the nucleophile comes in after the formation of the carbocation, the reaction rate is not affected by the concentration or nature of the nucleophile. So the nucleophile has no effect on the rate of reaction. Solvent is critical in SN1. So we're going to do this reaction in some sort of solvent. What kind of solvent works best? Well, if we can stabilize that carbocation and keep it in the carbocation form long enough for the nucleophile to finish the reaction, then we have a much better reaction. Let's take a look at solvation. Solvation of a carbocation by water. So if we have this in water, our carbocation can be basically shielded with water, which keeps it in the carbocation form longer, so then the nucleophile can come in and get it. So we actually, in an SN1 reaction, we want solvation to happen because it's keeping our carbocation nice and stable, whereas when we had an SN2 reaction, the solvent went around the nucleophile and just blocked it from reacting. Polar solvents promote ionization. Dielectric polarization P, solvent polarity. The ability of a solvent to act as an insulator of electric charge. Nonpolar solvents have low p-values, such as ethanol, where polar solvents have high p-values, such as water. SN1 reactions are favored in protic solvents. Remember, they are disfavored in SN2 because the transition energy is stabilized by solvation. When we use a polar solvent, this delta G is lowered, and we can have the reaction happen quicker because our activation energy, the energy required to get to the step, is lower. We have our carbocation formed here, and our polar solvent keeps it stable. Polar solvents are favored in SN1 because the carbocation is formed, where in SN2 it's disfavored because it keeps the nucleophile from doing its job. Now we're going to look at elimination reactions. We're finished with substitution for a bit. Alkyl halides, elimination. When we have an elimination reaction, a couple of atoms are going to be leaving our molecule, forming a multiple bond. Attack of a nucleophile at a neighboring hydrogen causes the elimination of HX to form an alkene. Zaitsev's rule for elimination. In 1875, Zaitsev figured out that when you have a reaction, in this case our example shows us bromine is on carbon number 2, that you don't get an elimination to the left-hand side of this carbon or the right-hand side carbon as products equally. In fact, one is favored over the other. Zaitsev wanted to figure out why. In an elimination reaction of HX from an alkyl halide, the more highly substituted alkene product predominates. What's meant by highly substituted alkene? If you look at the carbon-carbon double bond, those two carbons involved in that, if it has 4 R groups around it, it would be tetrasubstituted. If it has 3 R groups around that carbon-carbon double bond, it'd be trisubstituted. 2 would be disubstituted, and 1 monosubstituted. Let's talk about highly substituted. Let's take a look at the difference here. Here we have this carbon-carbon double bond, and this side has 1 R group, and this side has another R group. So this would be a disubstituted alkene. In this case, I have no R groups on that side, 1 on this side, so this would be a monosubstituted alkene. 2-butene is more highly substituted than a 1-butene, so you'll get more of 2-butene according to Zaitsev's rule. What products would you expect from the elimination reaction, and which is the major product? Go ahead and pause the video, write out your answer, come back and check your work. So we can see that this carbon here would have an elimination to the left of this carbon written, so we'd have an elimination product here and here. And since these 2 R groups are the same as each other, we're going to go ahead and represent that elimination to just the right-hand side. So we would get an elimination here and an elimination here. Which one is more highly substituted? Well, let's go ahead and count the R groups. So we have 1 R group on this side, and we actually have 2 R groups on this side. So this would be a trisubstituted alkene. Here's my carbon-carbon double bond again. I have no R groups here, 1 here, and 1 here. So this is a di-substituted. This one written first with the 3 R's is more highly substituted. That would be your major product. Okay, let's take a look at E2 reactions first. Elimination 2. Elimination bimolecular. This occurs in tertiary alkyl halides with bases, secondary alkyl halides with strong bases, and sometimes we can get the primary alkyl halides to work, but you need an extremely strong base. The reaction takes place in one step, just like the SN2 reaction with no intermediate. The base abstracts the hydrogen from one carbon at the same time the leaving group departs the neighboring carbon. It's a second-order kinetics rate law. And as we can see in this illustration, the base is going to come in. Base has its lone pairs. It's going to come in and grab this hydrogen. The pair of electrons that was holding this hydrogen and this carbon are now going to be given to the carbon-carbon bond, forming a pi bond there, a double bond. Too many bonds to carbon here, so the pair of electrons is going to go to this halogen here. This reaction is best for secondary and tertiary halides. The E2 reaction is very dependent on the orientation or the conformation of our starting material, of our carbon that has the halogen that wants to get out of there and be eliminated. We have a carbon-carbon single bond and there's free rotation. The best time for this reaction to happen, and when it happens, is when you have our hydrogen and our leaving group anti-periplanar. Taking a look at it from the Newman projection, you can see our hydrogen is straight up, and coming back and behind and straight down would be our leaving group. Anti-periplanar geometry is required where H and X are on opposite sides of the molecule. Anti-periplanar allows orbital overlap and minimizes steric interactions. So this illustration is showing you the orbitals and how everything's put together. So this is before the reaction. Our hydrogen is now anti-periplanar to our leaving group. We have our base coming in, holding on at the same time as our leaving group. So we have two things together at the same time. And then we can have the pi electrons being formed for a double bond, and the leaving group is gone. The mechanism of E2. A proton is transferred to base as the leaving group begins to depart. The transition state combines, leaving X and the transfer of a hydrogen. The base comes in, it grabs this hydrogen, but remember, this is all going to happen at the same time. The hydrogen is going to give its electrons here, and then too many bonds to carbon, so it gives its electrons here. So instead of this breaking up into pieces, what happens during the transition state is we actually have the electrons being delocalized over this entire step. So we have two things together at the same time with one transition state. They're all together at the same time. Then what's going to happen is the leaving group, hopefully it's a really good leaving group, is going to get out of there, and then we have our elimination product. It's this transition state you definitely want to know about when you're thinking about an E2. Again, this is one of the pieces that helps me understand the differences between E1 and E2 is this transition state. Everything's together at the same time. Elimination from cyclohexanes. Abstracted proton and leaving group should align trans-diaxial so they can be anti-periplanar in approaching the transition state. Here we have the Newman projection of the chair, and we have our halogen, or our leaving group, coming down here, and anti-periplanar behind it is this hydrogen. So this carbon here, and the carbon we can't see behind it, these are the two carbons that are going to be involved in the elimination step. A base comes in, we have an E2 elimination, and now we have cycloalkene formed. When we have equatorial groups, they're not in proper alignment. So this only happens with the trans-diaxial groups. Deuterium isotope effect. They use this experiment to prove and provide support for the E2 mechanism. They substituted deuterium for hydrogen at the alpha position. The alpha position is one away from the carbon that's going to undergo the reaction with the leaving group. So this would be one away. So this would be the alpha position. So instead of having hydrogen here, they put deuterium here. The rate is reduced in an E2 reaction. The heavier isotope bond is slower and weaker to break. This shows that the CH bond is broken before or in the rate-limiting step, as in one process. The E1 reaction. E1, elimination, unimolecular. This occurs with tertiary alkyl halides in polar non-basic solvents. First order kinetics rate law. The reaction takes place when the substrate spontaneously dissociates to yield a carbocation in a slow rate determining step before losing H+ from a neighboring carbon in a second step. It does not show the deuterium isotope effect. In an E1, we have our halogen or our leaving group here, and that's going to get out of there and form a carbocation. And we've learned earlier that carbocations are best with more R groups, so the best carbocation would be a tertiary carbocation. So this says this is best for tertiary halides. This is an example of a tertiary halide. After the carbocation is formed, then the elimination can happen where this hydrogen becomes eliminated and we have a carbon-carbon double bond formed. E1 mechanism. The elimination begins with the same unimolecular dissociation as in SN1, but the dissociation is followed by the loss of H+. Chloride, our leaving group in this case, leaves in a slow rate determining step forming the carbocation. After the carbocation is formed, the base is going to come in and take this hydrogen. It's the alpha position. The alpha hydrogen is one away from the carbocation. The pair of electrons that was holding this hydrogen and carbon is going to now form the pi electrons for the carbon-carbon double bond in a fast step, forming our alkene. The E1 reaction competes with SN1 and E2 with tertiary centers whenever an alkyl halide is treated in a protic solvent with a non-basic nucleophile. The best E1 substrates are also the best SN1 substrates, and a mixture of substitution products is obtained. We see here in this reactant we have a tertiary halide, water, ethanol, and 65 degrees C. We actually get a mixture of products. We get a substitution, and we also get an elimination. Stereochemistry of the E1 reactions. E1 is not stereospecific, and there's no requirement for alignment. The product has Zaitsev's orientation because the step that controls the product is the loss of the proton after the formation of the carbocation. Comparing E1 and E2. A strong base is needed for E2, but not for E1. E2 is stereospecific, E1 is not. E1 gives Zaitsev orientation. Summary of the reactivities of SN1, SN2, E1, and E2. Alkyl halides undergo different reactions in competition depending on the reacting molecule and the conditions. Based on patterns, we can predict likely outcomes. Here's a summary of substitution and elimination reactions, and if we have a halide that's primary, secondary, and tertiary, we can see in an SN1, a primary alkyl halide will not undergo an SN1 reaction. That would be a substitution where a carbocation is formed, and we know that a primary carbocation is not very stable. When we have a secondary carbocation, it can undergo an SN1 reaction, and it can also occur with benzylic and allylic halides because a secondary carbocation is formed, which is somewhat stable. With a tertiary halide, this is favored because the tertiary carbocation is extremely stable. SN2 reaction favors a primary alkyl halide. In a secondary alkyl halide, it occurs in competition with E2, so we can get a mixture. And a tertiary alkyl halide does not undergo an SN2 reaction. Elimination 1, E1. Primary alkyl halides do not undergo an E1. An E1 can occur with secondary alkyl halides with benzylic or allylic halides. And an E1 with tertiary competes with the SN1 reaction. In an E1 reaction, carbocations are formed, just like in the SN1, and that's why we see them competing with them. E2, primary alkyl halides, occurs when strong bases are used. E2 with secondary needs strong bases also. And E2 is favored with any kind of base when you have a tertiary alkyl halide.